is less, cross section of conductor is small, supporting structure and foundation are simple and light, but so it needs a higher insulation. This means, so we know that, so for constant power, so P is equal to V into I into cos phi. For same power, here we increase the voltage, then so automatically the current value decreases. If current value decreases, the cross section of conductor value decreases, that is a small value required. If cross section area is decreases, the weight of the conductor reduces. The lightweight conductor can supported by lightweight the structures, thereby overall system the cost is reduces and the easy design, but due to the increased high voltage we require the high insulation. So, this is a one drawback. And second one, due to the 25 kV system, line current is less and voltage drop is less, which improves the regulation. Already we have seen this one. And so, flexibility in the location of substation, because due to the high voltage we can erect the 50 to 80 kilometers. So, we can erect in this range anywhere due to the high voltage. And simplicity of substation design, lower cost of fixed installations, higher coefficient of adhesion, that is the mu, high efficiency. These are the some merits of AC system. Now, let us see some motor used in AC system. First of all, you can see the AC single phase series motor. Its full name is compensated series type commutator motor. You can see is details, construction details. It has similar to the DC series motor. Armature, it has you can see here, this is the armature, this is a pole shoe. Here one thing you can remember, the number of turns of main field is less, thereby it produces a less flux. Due to the production of less flux, the air gap between the rotor and stator is very minimum. And here is another winding, the green color, that is a compensating winding. The compensated winding may be in series with armature and series field, or sometimes it may be different. Here single phase AC supply is given to that one, it develops the similar characteristics of DC series motor, but it is not efficient as comparing to the DC series motor. You can see the equivalent diagram of the compensated series type commutator motor or single phase series motor. So, here the main winding, armature and compensated winding is connected in series. And so, similar, so another connections, so you can see here. So, this is another type. So, here main winding armature is connected in series, and whereas the compensated is connected short circuited. This is another type of arrangement. And what happened due to this one? So, if the any armature current flowing through the armature conductors, it develops some field. Due to this field, there is a possibility of armature reaction effect. This can be reduced by so compensating winding. Due to the transformer EMF, it induces some EMF in the closed circuit, and it develops the current flux due to the current. This field is in a similar position, it opposes the flux produced by armature conductors, thereby it reduces the commutation problem. And you can see the characteristics of AC series motor. This is similar to DC series motor, but it is inferior. You can see for the constant torque, the speed should be very low in case of the AC series motor. And these series motors can be used in most of the traction motors. So, this is the one application of our single phase series motor. Now, so what are the merits of single phase series motor? In single phase series motor, its operating maximum voltage is 400 volts and power factor is 0.95 lakhs at high speed. When it is running at high speed, the power factor as well as the efficiency increases. The compensated winding main function is to cancel out the magnetic effect of armature current. Air gap is very small due to weak field. We know that the number of turns on the main field is reduces small values. And to reduce the transformer EMF, which is the source of commutation troubles, these motors are run preferably from low voltage, that is 300 to 400 volts at reduced frequency 16 2/3 or 25 Hz. To reduce sparking, the brush width is kept small. In commutator, the width of the brush is small and the best suited for mainline services because its starting torque is somewhat inferior. So, it can best used for mainline services. Even then it has some advantages, it has some drawbacks. For a given HP AC series motor, the weights 1.5 to 2 times the corresponding DC series motor. You can see here. For example, if you are taking the 100 HP of DC series motor, 100 HP of AC series motor. Let us assume the weight of the DC series motor may be 500 kgs. For the same rating, for the same operational conditions, the weight of the AC series motor may be 750 kgs to 1000 kgs. That means, so at manufacturer at level also the weight of the AC series motor is more as comparing to our DC series motor. And next, the starting torque is poor, so it is not suitable for urban and suburban services. So, let us go to another AC system, that is a 3-phase AC system. At a glance you can observe it is a 3-phase overhead line running over the track. Here similar to the previous one, it takes a high voltage from the APSB people step down to 3.3 kV 50 Hz. Here is a frequency converter is required to reduce the frequency to lower value. What are the advantages for the due to the lower frequency? We know that. And this 3.3 kV at reduced frequency 16 2/3 Hz is given to the 3-phase overhead lines. So, here is a train. For clarity I given the 3 pantographs, but instead of this one only one pantograph with insulation, so collect the 3-phase supply, and this 3-phase supply is given to the traction motor 3-phase induction motor through control circuit. Let us go to 3-phase to single phase to 3-phase conversion system, that is a condo system. So, 3-phase overhead lines, due to this one there is a problem of at crossing. There is a problem at crossing and we require the 3 overhead lines. It can be reduced by the condo system. Generally the system is used in local trains, you can observe. So, how it will, you can see here, same the EHD substation. So, supply to the transformer is stepped down to the 16 kV 50 Hz, or sometimes the latest is a 25 kV at power frequency. This voltage is given to the overhead transmission line. From that the 3-phase induction motors collects through the transformer and converter. The single phase is converted to 3-phase supply, and from 3-phase supply to is converted to the low voltage for rating of traction motors. We know that is a very poor the starting torque as compared to the even slip ring induction motor, but it can get high starting torque due to low frequency, and high starting torque is very high without excessive current. That means here, so due to the with low current we can get high starting torque. How it is possible? So you can see here 3-phase AC system. So it is a practical example. This is a one feeding substation and is a train. So you can see the R, Y, B phases over the transmission lines. So this is a one type of the 3-phase induction motor locomotive. So inside we can use these 3-phase induction motors. And induction motors at a glance you can observe. So we well known these induction motors. These are some induction motors practically, and we know that it is a basic characteristics, it's a torque speed characteristics, this one, and it has the simple and robust, almost the constant speed, but we not required in traction. So it is a practically, you can see these are the few traction motors manufacturing for traction motors. So how there is a winding, you can see here, this is a rotor, this is stator, and it's a winding. And if the size of the induction motor is increased, so it can split it into the number of parts. So you can see it is a 1/3 part and it is doing the winding. This is a one type of the traction motor, and same this traction motor can be used in local trains. This is a one application of 3-phase induction motor. And so what are some merits? How we are going to get the high starting torque? You can see here some features of 3-phase induction motors. It has high efficiency and power factor when it operates nearer to synchronous speed. And last slide we have seen the starting torque is high due to the without drawing any extra current from the supply. How it is possible? So it is possible, you can see here rotor current, let us assume the rotor current I2 is equal to some constant slip, frequency and rotating magnetic field. Similarly, the torque is equal to some constant rotor current and field. I2 value substituting in this equation. So we can get K into phi square slip frequency. If frequency is reduced for the same constant torque required, then automatically we require to increase the magnitude of rotating magnetic field. Then same proportion to the current. Here the frequency is reduced, the increase in proportion to the magnetic field is less, thereby the current is less. So we can get our required torque, then the current is taken from the supply is same. And you can see the characteristics. So actually the basic characteristics of the series motors. So torque, speed, this is a starting torque of induction motor. When it is going to the high speed, the torque developed is more, and is a stable operation, is an unstable operation. But in traction motors we require the high starting torque initially only. How it is possible? So it is possible by the reduction of frequency, then automatically the torque, this curve will move towards the left. Thereby at that time this starting torque, if you are moving this direction, it may be starting torque, it may be starting torque, it may be starting torque. So that means the torque produced can be controlled by simultaneously controlling up magnitude of rotating magnetic field and frequency. If flux and frequency is controlled, then the motor will have excellent for the traction motor, and it has different advantages, merits, that is great mechanical strength, excellent power by weight ratio, suitability of high speeds, no sliding contacts required, high starting torque possible without overload, trouble free operation, less maintenance cost, high voltage operation at low current, and automatic regeneration is possible. Even then it has some drawbacks: flat speed torque characteristics, constant speed operations, difficult in speed control, and it requires more than one overhead line in case of 3-phase. So these are not required for the traction purpose. Let us go to control of traction motor by auto transformer. Here the well familiar with auto transformer, generally we are using in laboratory. So, if I taking the single phase from the overhead line is the auto transformer, here is a power transformer, here is the output. From the power transformer, so generally the tappings are provided on power transformer. If I require the high voltage at power frequency, so tappings are provided on HV side. If the frequency is less and low voltage, so we can provide, this is provided on LV side. You can see its merits. So, control of generally the control of traction motor by auto transformer, tap changing of high voltage AC traction system at power frequencies generally through an auto transformer. In low frequency system, the trappings are provided on LV side. For DC purpose, we require the rectifiers and filters at the secondary of auto transformer. So, in this class, so here is a question for you. So, you can answer my speed of the motor is 256.894 miles per hour. You can expect how much speed. So, in this class, we have discussed about what are the requirements of traction motors and different traction motors and how we are going to control the traction motors by auto transformers. Okay, let us see